This is Mary Green from Team 6978M. This video demonstrates Monte Carlo localization and how it can be used to improve autonomous navigation on a VEX field. On the screen, the red rectangle represents the robot's actual position and orientation on the field. The small squares around it are particles. Each particle represents a possible guess of where the robot might be, including both its position and the direction it's facing. This simulation uses 400 particles specifically, but in a typical VEX scenario, you can get away with about 100 to 200. We personally use 150 on ours. At the start of autonomous, the robot doesn't perfectly know where it is. Even if it starts at a node tile, small placement issues and wheel slip introduce uncertainty. That's why the particles begin spread out across the field. As I move the robot, all of the particles move as well. This motion comes from odometry, the same information we use in VEX from wheel encoders and an inertial sensor. However, each particle also has random noise applied to its motion. This represents real-world effects like inconsistent acceleration, drivetrain friction, and wheels slipping on tiles. Now, odometry alone isn't enough because error accumulates over time. To correct that, the robot uses distance sensors to understand where it is relative to the field. On our robot specifically, we use 3 distance sensors, one on the left, one on the right, and then one angled at 45 degrees coming off of the right side. This sensor placement is intentional. The left to right sensors help constrain sideways position relative to field walls, while the angled sensor helps resolve ambiguity near corners or diagonal field elements, specifically like the short goals on the pushback field. In the simulation, each particle predicts what those sensor readings would look like if the robot were actually at that particle's position. Those predicted readings are compared to the robot's real sensor measurements. Particles that closely match the sensor data receive higher weight, while particles that don't match lose weight. You can see that happening here. Particles that would place the robot inside walls or far from field elements quickly disappear. The remaining particles begin to flow around obstacles and cluster together. This clustering represents increasing confidence in the robot's position. The blue circle marker represents the estimated pose of the robot. This is calculated by averaging all of the particle positions and headings. As the particle cloud becomes more concentrated, the estimated pose closely follows the robot's true position. This entire process runs continuously during autonomous. Every time the robot moves, odometry updates the particles. Every time sensor data is read, the particles are reweighted and resampled. Instead of blindly trusting encoder values, the robot is consistently correcting its position estimate based on the field layout. In a VEX autonomous routine, this estimated position is passed into PID control loops. For example, PID may take the estimated heading to use accurate turns, or the estimated X and Y position to drive to a specific tile, which is then used in pathfinding code. Line up with a goal or approach a game element consistently. Monte Carlo localization makes those PID loops more reliable by reducing drift and correcting accumulated error, which leads to more repeatable autonomous routines. This visualization exists to make that process visible. You're not just seeing a robot move, you're seeing uncertainty collapse into confidence in real time as the robot navigates a VEX field. This project as a whole demonstrates how probabilistic localization can make VEX autonomous routines more reliable by correcting for odometry drift in real time. By combining sensor data, field geometry, and PID control, the robot can consistently understand where it is on the field. And that consistency is what makes repeatable, high-scoring autonomous runs possible. Thank you very much.